Hello, I'm Jackie Cation. Welcome to NASA's Universe Unplugged live chat, where NASA scientists are here to answer your questions and mine about our videos where the stories are fiction, but the science is real. Today we're talking about exoplanets. That's planets orbiting outside other stars. It's orbiting not our star, but other stars. As seen in our video, the habitable zone, scorched Earth enigma. You can find links to our YouTube channel on universeunplugged.org and downloads for each of our videos. There's all sorts of bonus information. Don't miss an episode by subscribing to universeunplugged.org and the YouTube channel, and that'll be super fun. And follow us on Facebook. You're watching us live on Facebook Live, and join future live shows and know about them in advance. Today, we are joined by Dr. David CRD, who is the chief scientist at NASA's Exoplanet Science Institute. He is a member of NASA's Kepler and TESS exoplanet discovery mission team, and his research focuses on the fundamental nature of stellar variability and the relative sizes of planets in multi-planet systems. Look who knows how to read. This one, Jackie Cation. Welcome.
Well done. Thank you, Jackie.
We're also joined by Dr. Robert Hurt, who is an astrophysicist at NASA's Spitzer Science Center. He specializes in visualizations of scientific observations, and he wrote and directed the Habitable Zone episodes for Universe Unplugged. Hi, Robert.
Hi, Jackie. And hi, David.
Hey, Robert.
There we go. Let's start with a clip from the Scorched Earth Enigma before we dive into the questions.
You ready to bring us into the habitable zone?
Let's see if the telescopes can find any Earth-sized planets around here. I said I'm working. I'm looking here.
Like those?
I'm trying. Well, what do you know? Planets. Everything here's all bunched up around that star. There's a large planet right next to it over there, a couple more further out.
And one right smack in the middle of the habitable zone.
Hang on then. Taking us in.
Okay, so that is a clip. You can watch all the videos at universeunplugged.org and on YouTube. But let's quickly review what we usually mean when we say the habitable zone. David, can you do that?
Yeah, absolutely. So the habitable zone is as planets orbit their stars, there are certain regions where it's super hot, like as you get very close to the star, it's really, really hot. And as you get away from the star, it can get really, really cold. And there's a zone in the middle where we think it's just the right temperature where liquid water can form. And we're pretty sure that liquid water is necessary for the sustainability and the habitability for life. At least that's true on the Earth. And so if you move in too close, all the water goes away. If you move in too far out, all the water freezes. And the place in the middle where you have liquid water, that's where you can have life. And so we think the habitable zone is all these regions around all these other stars where we think if there's a planet there, it might potentially have liquid water.
Okay, so are we looking for stars like our sun? So only stars like our sun can support planet. Are all stars like our sun, Robert? Talk to me.
Well, actually, we are very, human-centric and geocentric, and we look up and we think like, okay, well, there's the sun, and all stars must be like it. But in fact, stars can be really, really different. Stars can actually be a lot larger, and they can be a lot smaller. In fact, our sun isn't even especially common in the universe, right? It turns out as you get to smaller and smaller stars, those are actually a lot more numerous. And in the habitable zone video, you had a question, Jackie, to follow up?
Yes, quick question. Are all stars made out of the same gases? No.
Yes. Okay. So for the most part, yeah, they're all more or less made up of the same stuff. It's mostly hydrogen, a little bit of helium, and then some trace elements mixed in with that. Now, I'll put a caveat: the very, very first stars probably just had the hydrogen and helium, but that's a different podcast. But yeah, basically stars have more or less the same material, and it's mostly hydrogen. And they're defined because that hydrogen gets so compressed in the core that it allows nuclear fusion processes to occur that actually like turn the hydrogen into helium and then eventually helium into carbon, things like that. That generates energy and that makes the stars glow. But what's cool is that you can actually do this with a star that has a tiny fraction of the mass that the sun has. And whereas our sun is like really, really large compared to all the planets in our solar system, if you go on the low end of stars, you get stars that can be as small as basically about the size or just a little bit bigger than Jupiter. Now, point of context, Jupiter is about like 1/10 the diameter of our sun. So there are stars that are so small, they're basically, they would look like the size of the planet Jupiter. And that was the kind of star that we were showing in that clip from the habitable zone, one that's a lot smaller and a lot cooler, and would still generate light and heat, would still have a habitable zone. If you get to the right distance from something that's small and cool, it'll still be warm enough potentially to support liquid water. But yeah, so there's a lot of different kinds of stars out there.
Okay, and so David, can you talk a little bit more about why, if we're only going to go, we're not going to go around looking for planets on stars that are the size of our sun, what do we need to do why would we look for planets around stars that are not like our sun? I guess there's been some explanation, but I'm still...
That's a really excellent question, and it's actually, and it's something that Robert just alluded to, is that the universe makes stars in all kinds of sizes. So there's really big stars, and there's really little stars, and there's middle-sized stars. And our sun is kind of a middle-sized star. And just like people building buildings, it's easier to build small things than it is to build big things. And so there's a ton more small stars than there are big stars. And so we often search for planets around small stars because they're so numerous. And if we can find a planet that has life on a planet, if we can find a planet around a small star, and that planet might be habitable at some point, that might suggest, oh, life is everywhere. And that would be super cool. And so one of the reasons that we study many kinds of different stars and search for planets is to really understand how common are planets and how common is the possibility for life in the universe.
Wow.
And
yes, Robert.
I was just going to throw a follow-up to that too. Another reason that we're actually interested in looking for planets around smaller stars is it actually also makes it a lot easier to find smaller planets, right? Like one of the techniques we use to detect planets, in fact, the most common, the largest number of planets found have been because we look at the light from a star and we see like when a tiny little planet passes in front of the star, it blocks a little bit of the light. And obviously, if you're working with a small star and you're passing something the size of the Earth in front, it actually is going to block a larger fraction of the star's light than if the star is 10 times as big. It's always easier to detect maybe a 1% variation than like a 1/1000% variation or something like that. So it turns out we actually have an easier time finding Earth-sized planets around small stars than we do finding Earth-sized planets around stars like our sun.
Okay, and is our sun sort of a medium-sized star in the course of stars, or I mean, I don't know.
Yeah,
it's obviously
absolutely,
a large.
Yeah, so absolutely. So our sun is about mid-range in both size and in age. So the universe is about 10-ish to 15 billion years old. Our sun is about 5 billion years old. Stars range in mass from about 10 times the mass of the sun to about 1/10 of the mass of the sun. And so our sun really is middle-aged, middle-sized, porky kind of star.
This Goldilocks thing it makes more sense every episode. I'm just like, oh, I see why the Goldilocks is the analogy that scientists are using all the time. I was thinking about doing sort of a more in-depth question. We also have people can ask questions. There used to be a hashtag that was up on the screen, but here, if you guys want to do ask UU live, we can do. I could take questions, but how about this one? In the video that you can watch at universeunplugged.org and on our YouTube channel, the Scorched Earth Enigma, they find a planet that is the right temperature, but it doesn't have an atmosphere to support life. and they compare it to Mars. Is that what really happened to Mars? Either one of you, what do you think?
So
Go.
so possibly. So we know that there is water on Mars, and there used to be much more liquid water on Mars, and that is now gone. And so what we think happened was that Mars, like the Earth, was bombarded and had liquid water. But Mars is much, much smaller, and so it can't hold on to its atmosphere the way that the Earth can. And so the atmosphere eventually evaporates off, and then the water evaporates, and the water goes away, and there's nothing to hold on to it. So eventually, over the course of hundreds of millions of years, which is a tenth of the lifetime of the solar system, Mars most likely lost and most traces of water, and the only water that's left is probably trapped in the rocks or underground. And so, yeah, it's quite possible that Mars really did have water. There are channels that we see in the ground that look like they were carved out by flowing water. And so the possibility that Mars did have water and it all eventually evaporated off is quite possibly true.
Okay. And we did get a question from the internet, which was, how unique is the Earth? You want that one, Robert?
Sure. I guess you can certainly say every planet is unique, right? They're all snowflakes. No two moons, planets, anything in our system is exactly alike. But the fact that Earth has such the right balance of everything, where it's orbiting at that right distance from the star to support liquid water, it has enough water on its surface to provide oceans, and has had that for basically the length of its history, since it formed. It has a lot of factors that are lined up precisely correctly. When you go and you look at the catalog of planets that we found around other stars, we have not yet found a planet that is exactly the same size as Earth, orbiting a star just like the sun, at that exact right distance that the Earth is. Right? We found planets that are the same size as the Earth, but orbiting, either too close or too far away. We found planets the same size as the Earth orbiting in the Goldilocks zone around different kinds of stars. We found planets that are bigger or smaller around stars like the sun, orbiting in the Goldilocks zone, right? There's so many variations, right? But yeah, we haven't yet found something we can point to and say, hey, that is exactly like the Earth as far as we can measure so far. So
if
treat this one carefully. It's special.
Yeah, but if we did, wouldn't it, by definition, then be habitable? I mean, like, we haven't found anything else that's habitable, right, David?
Right.
Yeah. So we should be really clear. We found nothing that we know that is habitable. We have found planets that are in the right place that they might have liquid water, and that makes them interesting. But that's not the same thing as knowing that they have liquid water, and it certainly is not knowing that they are habitable or even inhabited. Habited is not a word. And so what we're finding right now is planets that we think might be of interest or might have similar properties that the Earth has, both in terms of size or in terms of temperature, but we're still really on the cusp of trying to find those planets. So as Robert pointed out, the universe makes planets and solar systems in all different kinds of varieties, and our solar system is just one. And so finding something that is just like our solar system or just like our Earth takes a long time of searching, because it's pretty clear to us that the universe makes solar systems in a variety of ways, in a variety of configurations, of which we're not, we're just now understanding and exploring.
Right, and we're exploring it via telescopes, right? Obviously.
Absolutely, yeah. So if I could have that spaceship in the clip that Robert directed and writ, I would take that spaceship in a heartbeat and go, but we don't have that yet. So Robert, get on that.
That was part of the dream of this, is if we could actually carry our telescopes and really drop them right down into a system and study it. It make it much easier to do what we're trying to do today remotely. But that's actually, I wanted to comment, that was also comes back to this idea of we have a lot more stars that aren't like the sun, small stars. They're more numerous. But I made a comment that was also easier to detect planets around about the size of Earth around them. And one of the reasons that's true is that the habitable zone around a small star is so much closer in that a year on a planet like that is only a few days long, a few days, a dozen days, or so forth. And so given that one of the ways we look to detect planets is we wait for it to pass in front of the star again and again and again, obviously if a planet passes in front of its star every 10 days, it's going to be a lot strategically easier to see it, produce it, reproduce the result, watch it through a lot of transits and say, oh yeah, we definitely found something, than a star like the sun, where a planet the size of the Earth, orbiting in its habitable zone takes a year to go around. And so, around a small star, you can do, 10 years worth of work in a month or two in terms of detecting the planet. So it's not that we don't think there are other planets like Earth out there. It's just that it does take a lot more time and a lot more precision to find something like that. So it's a waiting game, and it's building the instruments that will keep letting us do this, that will hopefully let us find, by someday, many, many other planets very similar to the Earth. At least
okay, that makes perfect
overall
sense.
properties.
Yeah. Okay, let me just say that if people are just tuning in, if you missed the beginning of the show, we're chatting about the science in the NASA video, The Habitable Zone Scorched Earth Paradox, which you can see at universeunplugged.org, or just click on the link in the comments. And so in the video, before I asked my question, in the video, Kara figured out that the kind of star that they were orbiting by looking at a graph. In the graph, it looked like science fiction graph, squiggly lines. Is that based on actual? I mean, you made the video, Robert. Is that technobabble, or is that really how what you're using to identify stars?
So in the video, as much as possible, even though we made up a sci-fi setting to put them on a ship and fly them into another system where they could go and fly up to planets that are around other stars, we still were trying to make the science as real and relevant to how we do science from Earth. And it turns out that the way that you identify what kind of star you're looking at is you take the light from the star and you break it up into a spectrum. It's like passing light through a prism, and it breaks it up into all the colors of the spectrum, both the parts of the spectrum we can see and the parts that we can't. Infrared light, ultraviolet light. And by looking at how the brightness of the star changes at different parts of the spectrum of light, that's basically the fingerprint. It tells us a lot about the star. It tells us what materials are in the star. It tells us how hot the star is, and then from that and our models of how we understand stars are built, we basically can figure out how big the star is and how much mass it has, where its habitable zone would be. And so the little figure that Kara was looking at was actually real spectrum data. I mean, that's kind of what a stellar spectroscopist would do. They'd look at the squiggly lines and figure it out from that.
Wow. Could you please say that word again? What is it?
A stellar spectroscopist.
Thank you very much.
I don't know if that's officially what they call themselves, but yeah.
Okay. So Dr. Ciardi, let me ask a science fiction question. Yeah. If you watch Star Wars, you know that in the Star Wars universe, every planet has just one ecosystem. There's a desert planet, there's an ice planet, and there's a jungle planet, right? If we are talking 4, 5, and 6, right? What is that?
And
thanks for playing. Yes.
And Endor, Forest Move Endor.
Yes. Okay. And is that likely? That doesn't seem likely, does it? What do you think the science is on that?
It's so hard to draw, those kinds of long extrapolated conclusions. It would not surprise me if there were planets that were significantly different than the Earth. But I would also imagine that there are planets that are a lot like the Earth. And so, it's hard to answer that question from a scientific point of view. I do know that, and I saw an interview of George Lucas, part of the reason he did that was he wanted to change color schemes. He wanted to go from brown to white to green, which is probably not how the universe makes planets.
I think
I would-
we know. Yes.
But it wouldn't surprise me, that if there was a planet that was coated in ice and snow, if there was a planet that was completely encoded in forest. I mean, all of that is all possible. We do know that we have different temperatures on the Earth, from the poles down to the equator, but that's a result of the shape of the Earth and the tilt of the Earth. And so Robert was going to say something.
Yeah, I was going to make the comment. I think it's probably really easy to make a complete desert planet because if you have something that's dry and way hot, you'll have it'll be very similar all over it. And likewise, making a nice ice ball certainly easy if it's really really cold and it's all kind of the same all around. But you even look in our solar system and you see like Pluto is this dwarf planet way far out. We sort of thought it would probably be just an ice ball that would be very, very similar all around its surface, but had a lot of varying terrain. There aren't many things we see in the solar system that are just exactly the same all over. Even Mars, which is mostly, you call it like a desert planet, has ice caps. The ice caps are actually more carbon dioxide than water, so they're a little different. But yeah, there are a lot of variation. But it's narratively, it makes a lot of sense to keep it simple and just say, oh, it's an ice planet or a water planet or a forest planet. But even the things that are very, very similar in composition in our system still have a lot of variation.
Right, and what I just learned was that it has something to do with the shape of the Earth and the tilt of the axis. So look at me learning. This is very exciting. I have another question from the internet. Oh, go ahead.
Oh, let me just jump in, because you can also run it all the other way. When you actually look at planets that are orbiting very small stars and they're very close to the star, there's an effect called tidal locking that we think could become an important factor, in the same way that the moon orbits very closely to the Earth, and we always see the same side of the moon as it orbits the Earth. We think that it's very likely that planets that orbit very close to their stars, a lot of them could be tidally locked. And so that the same face would always be pointed towards the star and the other face would always be pointed away from it. And on a planet like that, you would get extremely different conditions from one side of the planet to another. You'd probably have one side to be, at much, much higher temperature, baking in the sun. The other side would be frozen. And
full of Draculas.
And if you had and full of Draculas or Remans, if you're into Star Trek. And if you had a world like that was sitting in its habitable zone, you might actually end up with a situation where there might only be one narrow strip around the planet that had the right Goldilocks moment. So not only would the planet have to be in the Goldilocks zone, when you go to the planet, there might be like a Goldilocks band that's not too hot and not too cold, where maybe you could get liquid water and it might not be too terrible to live on. So in that case, it's
real estate prices would be really expensive.
Oh yeah.
Lex Luthor, buy land. Anyway,
that's right.
In the from the internet,
Did you just call me Lex Luthor? Wait a minute. Just call me Lex Luthor.
I would never, Doctor. It's okay. Here's another question from the internet. In terms of viewing exoplanets, what are the obstacles to having a space-based interferometer, and why don't we have one now? I'm gonna guess money.
So it's all about money, and it's all about the willingness of humans to figure out and do something. So there was a mission concept that started to get designed in the late 90s, and it went pretty far along in its design up until about 2008 or 2009. And the idea was to launch an interferometer in space, and it would measure the wobble of the stars as the planets orbited the stars. And it's a really tiny motion, but that's what it was designed to do, and it was designed to find Earths around sun.
And you want to define an interferometer quickly for them?
Sorry.
Just in case someone doesn't know what an interferometer is.
That's a good point. So an interferometer is two telescopes that are separated by a long baseline. So in this case, that interferometer in space would have been about 10 meters or about 30 feet apart. And so each individual telescope is pretty small, but the long baseline gives you super high resolution, essentially. and you don't need a big 30-meter telescope when you can just use the two small telescopes and then measure the relative position of the star in comparison to other stars around. At any rate,
where were they going to put it? Okay.
So it would have been in orbit. It would have been a Spitzer-like orbit where they would have pushed it away from the Earth, and it would have been in orbit around the Sun. And it was a lot of new technology. We had never done anything like that before, but it really came down to cost, and then at the same time, the technique that Robert was describing earlier, where we started to discover planets through the transit method, where the planets were blocking the light of their stars. That technique sort of came into its own at about the same time that we were developing this interferometer, and we realized that we could use this other technique, the transit technique, to find small rocky planets, and that technique, the spacecraft necessary to do that was less expensive than the space-based interferometer, and so there was a choice made, and not an unreasonable choice. So so it really
it'd be great to do both.
Yeah. So in the end, it often comes down to choices, right? That's life.
Yeah. Fair enough. Okay. I have this question, which was, so when we're watching the video, which is on universeunplugged.org or YouTube, they could just look at the planet and see that it didn't have any water. Is there any way for us to figure out with the data that we receive the composition of exoplanets if we can't see them? Robert?
So yeah, I mean, this is one of our biggest challenges right now, is we want to understand the composition and makeup, right? We don't want to know just a planet happens to be there, but we want to know what's on it, what's physically there. And so we have to use a lot of very indirect techniques to do this. And I mean, I'll talk about one example of a technique we can use to understand. If you can't see the planet and all you can see is the light from the star when the planet passes in front, what can you do with that? Well, if a planet has an atmosphere, then the atmosphere, there's a layer of atmosphere around the planet that extends, further out than the rocky surface. And that atmosphere will be made of something, right? It might be hydrogen, or it might be oxygen or nitrogen or whatever, right? And it turns out every element, every molecule has certain wavelengths of light that will pass through, and it will be transparent. We think of our atmosphere as transparent, but even things like oxygen, nitrogen, there are certain wavelengths of light that it's not transparent. It will actually block the light. So if the planet has, let's say the planet has an atmosphere of nitrogen around it, okay, there will be certain wavelengths of light where the nitrogen will stop the photons from going through. And so at those wavelengths, the planet will look a little bit bigger, because the transparent atmosphere won't be transparent anymore. It'll be opaque, like a big thick cloud. So if you can look at that, and water does it at different wavelengths. So if you can look at how much light the planet blocks at one wavelength of light and another and another and another, and you see that the apparent size of the planet seems to vary a little bit, that tells you can actually start to piece together what chemicals make up that atmosphere. And so, for instance, if you can do this for water vapor, you can actually deduce whether there might be water in the form of vapor in the atmosphere. And then that's, again, it's the beginnings of piecing together the chemistry of what could be going on in the atmosphere. That, of course, still won't tell us about what's actually happening on the surface, or whether there are lakes on the surface or oceans.
Okay, Dr. Ciardi?
I just want to add that one of the places that we're going to in the future, where we're trying to get to, is to be able to directly image the planets. So block out the starlight and directly image the planet, and then get a direct measurement of all the light from the planet itself. And so we would sort of do what Robert was talking about, getting a light analysis of the planet, but we would do it directly, and that would open up us to be able to do planets around all stars and not just ones that transit. But that's still many years away. We're still working on those technologies to enable us to do that. But that is the future direction of exoplanet astrophysics.
Wow, that is fascinating. This has been amazing, by the way. I have learned many things, as is the reason I do the show. Anyway, we have been talking with, of course, Dr. David Ciardi and Dr. Robert Hurt. Go to Universe Unplugged. Thanks so much for joining us to learn more about science of the universe unplugged. All of those videos are watchable on YouTube and at universeunplugged.com. You can go to Cool Cosmos on Facebook and like and join that so that you can find out when the next episode is. And the Habitable Zone, Scorched Earth Enigma, you can see that and all of our other Universe Unplugged videos at, like I just said, universeunplugged.org, or just click on the link in the comments. Subscribe on YouTube, and you'll be the first to know when the next video comes out. Follow us on Facebook. Catch the next live chat. Until next time, I'm Jackie Cation, and this has been Universe Unplugged live chat. Thanks a lot.
Hey, thank you. This was awesome.
Thanks.